Welcome, everyone. Okay, let's just dive right in. Today, we're taking on a pretty exciting mission for our Grade 7 pre-algebra journey. We are reviewing our mathematical toolkit for ratios, and then we're going to transfer those skills to solve some real-world mysteries. Seriously, whether you're dealing with prices at the grocery store, trying to figure out the best cell phone plan, or even just trying to beat a level in a game, proportional reasoning, it's kind of the hidden engine running the whole world around you.
So here is our roadmap for this explainer. First, we'll hit ratio and unit rate tools, then move right into proportional tables and graphs. After that, we'll spot some non-proportional relationships, transfer our skills to new contexts, and wrap it all up with a quick self-check. Let's do this.
Section 1. Ratio and Unit Rate Tools.
All right, to build our foundation, we really need to understand our most reliable tool, and that is the unit rate. A unit rate basically strips a complicated relationship completely down to its most basic form. It asks one very simple question: how much for just one? In math terms, you'll hear this called the constant of proportionality. It's a big, fancy phrase, I know, but it just tells you exactly how one quantity scales in relation to a single unit of another.
So the absolutely crucial point here is that magic number 1. Whenever you're dealing with unit rates, you are always trying to find the value out of 1. Because think about it, whether it's dollars per pound, miles per hour, points per game, identifying that single unit and its attached label is the absolute key to avoiding mistakes. If you know what just one unit is worth, you can scale it up to 1,000,000 or scale it down to a tiny fraction. All the power is literally in that one.
Section 2. Proportional tables and graphs.
Now, tracking the cost of notebooks perfectly illustrates exactly what happens when we start scaling up. This right here is a perfectly proportional relationship. Why? Well, because every single time we take our total cost, the y value, and divide it by the number of notebooks, our x value, we get the exact same answer. 3 divided by 2, 1.5. 6 divided by 4, still 1.5. We are consistently getting that exact same unit price of $1.50 per notebook. That is your constant of proportionality right there in action.
And because that relationship never changes, we can easily translate all that data into a really elegant tool, an equation. Our total cost, y, is just equal to our constant of proportionality, 1.5, multiplied by x, the number of notebooks. So, y equals 1.5x. With this simple rule, you don't even need a massive table anymore. If you want to buy, say, 100 notebooks, you just plug 100 in for x, multiply it by 1.5, and boom, you instantly know it costs $150.
But what happens when we visualize this? Well, if we graph this notebook relationship, the line absolutely must pass through the origin, right at 0, 0. This is basically the golden rule for proportional relationships. It proves that 0 notebooks will cost you exactly $0. Makes sense, right? If your line doesn't pass through that exact intersection of the x and y axes, then it is mathematically impossible for the relationship to be proportional.
Section 3. Spotting non-proportional relationships.
Okay, looking at this side-by-side contrast, it's actually super interesting. On the left, our notebook equation relies purely on the unit rate, y equals 1.5x. But check out the equation for a taxi ride on the right, y equals 2m plus 4. The taxi charges $2 per mile, which is our rate of change, but it includes an extra starting fee of $4. That little plus 4 at the end? Yeah, that changes the whole shebang.
Because of that starting fee, if you travel exactly 0 miles in that taxi, the meter already reads $4. You haven't even moved, so the graph completely misses the origin. Now, while this is still a perfectly straight line, meaning it's a linear relationship with a constant rate of change of $2 per mile, it is officially non-proportional. If you try dividing the cost by the miles at different points during that taxi ride, you aren't going to get a constant number. You have officially spotted the imposter.
Section 4. Transfer to new contexts.
We know how our tools work and we know when they don't. So we're going to apply proportional reasoning to something you see literally all the time in the real world, figuring out the final price during a huge store sale. Actually, fun fact, percentages are really just ratios disguised in a different format. The word percent literally means out of 100.
So, to solve percent problems using our toolkit, we just follow 2 super logical steps to make sure we don't accidentally overpay. First, we find the discount amount. That's the actual chunk of money they're taking off the price. Second, we subtract that chunk from the original price to figure out what we actually owe at the register. Simple as that. Let's look at an example together. Say you find a really cool shirt that originally costs $50, and the tag says it's 30% off. By treating the 30% discount as a proportional rate of the $50 whole, we can easily calculate that discount amount. 30% is just 30 out of 100, or 0.3, right? So we multiply our whole, 50, by 0.3, which gives us a nice, easy $15 price drop. Then we just subtract that $15 from our original 50.
Leaving us with a massive victory, a final sale price of $35. And notice, complete with our crucial unit label, the $sign. By just breaking the problem down and applying proportional rates, we transferred our toolkit into a completely new arena. And hey, we saved some money in the process.
Section 5. Time for a self-check.
You've equipped the tools, you defeated the non-proportional boss, so now it's your turn for a quick self-check to prove your mastery. I want you to pause this explainer right here and use everything we've just reviewed to solve this real-world grocery problem. The question is, if 5 pounds of apples cost $8.75, what is the unit cost per pound? Keep a really close eye on your units, think about finding that magic number 1, and go ahead and solve it.
Okay, you ready? If you took your total cost and divided it by the number of units, meaning dividing $8.75 by the 5 pounds to find your constant of proportionality, then you absolutely nailed the unit rate. It is exactly $1.75 per pound. Awesome work. You figured out exactly how much just 1 pound costs.
All right, to wrap up today's mission, let's just lock in the core takeaways. Remember, unit rates are your base tool, and they lead directly to proportional equations like y equals kx. You also know for sure that proportional graphs absolutely must start at the origin, 0, 0. If you see a totally different starting value, like that sneaky taxi meter, you are dealing with a non-proportional relationship. And above all else, always double-check and label your units. It'll make you unstoppable in pre-algebra and the real world.
So, as you look at the prices, the speeds, and the sales all around you today, I want you to ask yourself this. Where else might the math be tricking you? If a relationship isn't proportional, what other invisible fees, starting values, or hidden rules are just kind of built into the everyday choices you make? Use your new toolkit to uncover the truth. Keep questioning the numbers, and I'll catch you in the next one.